Hello everyone. In this lecture, we are going to study turbulent kinetic energy budget. So the TKE budget, we are going to use the Reynolds stress equation that we derived and just look at kind of one special case of this to derive the turbulent kinetic energy budget equation. Okay. So in order to do so, we define some parameters here. So the first thing that I define is Q square. So Q square, we define this as U prime I. So the multiplication of the fluctuation velocities by themselves. Okay. And then we define the turbulent kinetic energy budget or turbulent kinetic energy as K. And we define it as 1/2 of U prime I average, which is going to be actually 1/2 of Q square bar, which is actually going to be 1/2 of all the velocity components fluctuations. So U prime 1 squared bar plus this index again can be from 1 to 3, right? So we have U2 prime square bar plus U prime 3 squared bar or average of that. Okay, so this is actually like U1, U2, U3 could be also UVW, the three velocity components. We just take their fluctuation square and then average that, and this is kind of known as kinetic energy, but turbulent kinetic energy. Okay, we can also have mean kinetic energy, which I'm going to define as capital K, and it is simply 1/2 capital U, which is the mean velocity, UI, which is going to be 1/2 U1 squared plus U2 squared plus U3 squared. Okay, so this is mean kinetic energy. Okay. Mean kinetic energy, or we also call this as MKE. And this one is TKE, turbulent kinetic energy. Okay, so these are some definitions that we have, and now in order to find the turbulent kinetic energy, the equation for turbulent kinetic energy, what we are going to do is we can find it based on the Reynolds stress equation. So an equation for the fluctuating kinetic energy can be found from the Reynolds stress equation by contracting the free indices. So here we had this general way of that. So instead of k, we need to write it as I, right? So if we, instead of k, we write this equation as I, then we are going to get an equation for u prime I, right? Okay. So we set k to I, and we are going to get this equation, partial u prime I bar over partial t plus uj partial over partial xj of u prime I bar. So this is the left hand side. Let me make sure, yep, I'm correct. And then on the right hand side, we have this equals to the divergence term, which is partial over partial xj of minus 2 over rho p prime u prime I bar delta ij minus q squared u prime j bar plus 4 nu sij u prime I bar. Okay. And then we have other terms. So this is divergence terms, and then we have minus 2 u prime I u prime j bar partial ui partial xj minus 4 nu sij partial u prime I partial xj bar. Okay, so this is just set this equation k in this equation to I. And also another thing that we did here, the pressure strain term, the pressure strain rate, eliminated, that is eliminated due to the incompressibility condition, that is partial u prime I over partial xi equals to 0. We know that, right? This is the divergence of the fluctuating part. So because we have this, so when you have it and then you make I equals to k equals to I, so this term is going to be 0. Similarly, this term is going to be 0, right? So when these two terms are 0, then the whole pressure strain rate term that appears in the Reynolds stress equation is going to be 0 when we want to use it for turbulent kinetic energy equation, okay? So this is kind of a little bit simplified than the original Reynolds stress equation. And now I want to further simplify this equation. So let me write this one. Specifically, I want to further simplify this term, which we call it the dissipation term. Okay, so let's do that. So we can write the velocity deformation tensor. In general, we can decompose it into a symmetric part, symmetric tensor, and an antisymmetric tensor. How? So you can write this partial u prime I over partial xj, right? This is the velocity deformation tensor that we have here, okay? We can decompose it into a symmetric part. We can just write it as 1/2 partial u prime I over partial xj plus, add this term and just subtract it. So we are going to add u prime j over partial xi. So we add this term and then we subtract it later. So we have this plus 1/2, again this term because we want it to be there, partial u prime I over partial xj, and then subtract this term that we added, okay? So it's going to be minus partial u prime j u partial xi, right? So we can do that, right? It's exactly the same thing. We just added this and then subtracted this and then rewrote this in terms of 1/2, 2 1/2s, right? But the interesting thing about this decomposition is that now this part, okay, we call this, as we remember from last time, it is Sij, right? And it's a symmetric part. It's a symmetric tensor. And this is actually the strain rate. We call this a strain rate tensor. Okay. On the other hand, the other part, we call this, let's say, omega ij, which is anti-symmetric part, and is actually the rotation rate tensor. Okay, so we have decomposed the velocity deformation tensor into a symmetric and anti-symmetric part, right? And this is the good thing about this decomposition. Okay, now when we multiply Sij here, say for this term, by the velocity fluctuation, so Sij times partial u prime I over partial xj, and then take the average here, this equals to, so instead of the velocity deformation, I can write it as, again, the sum, so Sij times the sum of the Sij, the symmetric part, and anti-symmetric part, omega ij bar, right? So this equals to this, and this equals to, I can just expand the terms, Sij bar plus Sij omega ij bar, okay? And now we know that this term is going to be 0 because the double contraction, this is kind of a mathematical identity, that the double contraction of a symmetric tensor with an anti-symmetric center, anti-symmetric tensor, is identically 0. Okay, so we know this from some math theorems. So this will simplify the term in equation 1 here, this term, And we can simply write that as Sij partial u prime I over partial xj bar. This equals to just simply Sij bar. Okay, so this is just one simplification, and I want to get an equation for TKE, which is going to be 1/2 of this, right? 1/2 of this equation that we got, right? This is just a definition of TKE, how we define it. The turbulent kinetic energy is just 1/2 of that. So we need to divide this equation by half to get what we thought, right? What we thought. So divide 1 by 2, and we are going to get this equation for turbulent kinetic energy. So partial K over partial T plus capital Uj partial K partial Xj equals to the divergence term, which is partial over partial Xj of minus 1 rho P prime U prime I bar delta Ij minus 1/2 Q square Uj bar plus 2/2 Sij U prime I bar. Okay. And then we have the other terms, which are minus U prime I U prime J bar partial Ui partial Xj minus 2 nu. Instead of the last term, I can write Sij partial U prime I can just write Sij bar. It's going to be minus 2 nu Sij bar. Okay, so this is very important equation in turbulence. Very important equation, that is the transport of turbulent kinetic energy, or known as turbulent kinetic energy budget. So this is actually what we know as TKE budget equation. Okay, similarly, we can find an equation for the mean kinetic energy. Okay, so this was for turbulent kinetic energy, and we can similarly find an equation for turbulent kinetic energy. Let me write it down. So for mean kinetic energy, we can write the budget as d capital K over dt. Okay, so similarly, we can find an equation for capital K, mean kinetic energy, which is 1/2 UI. And it's going to be like this: dk or dt equals to partial over partial xj minus 1 rho p, capital P, ui delta ij minus 1/2 u prime I u prime j bar ui plus 2 nu sij ui bar plus u prime I u prime j partial ui over partial xj minus 2 nu sij which is for the mean component. Okay, and this is known as, so let me put it here. This is known as MKE budget. MKE, mean kinetic energy equation, budget equation. Okay, so TKE budget equation and MKE budget equation. So one of the things that you can see here, and we are going to discuss all these terms, what all these terms mean, and one by one. Okay, in the next session we are going to give some physical insight on these terms. But one thing that you can see clearly here is that this term appears in both of these equations, but with different sign. And we will see that this is kind of turbulence production. So the turbulence, when the turbulence is produced here, it's kind of reducing it from the mean equation. So from mean you get that gradient and then smooth it. The turbulence kind of, when you have gradients, you have some turbulence production, and then it kind of smooths the flow, smooths the gradients. Okay, so we will talk about these terms in the next session, but this is generally the equations, the very important equations for in turbulence for describing the turbulent kinetic energy and how it kind of evolves in time. Okay, so in the next session I'm going to go through each of these terms, especially in the TKE budget equation here, and I will explain what do each of these terms mean. One of them are like turbulence production, one is dissipation, and one is transport, the transport of turbulent kinetic energy.